Okay, so you're welcome from any part of the world you're watching from, right? You might be wondering why should you pay attention to this kind of learning pipeline or learning process, right? Now, this uh, live section, right, was primarily for my benefit, right? That's me being honest here. Right? It was primarily for my benefit, and it's just so that I can actually commit to being consistent or back end space. Right? You've not heard about Linux before. You've not heard about server before. What a server is. You've not heard about what a virtual machine looks like or what it is. You don't know what CPU means. You don't know what GCPU means, right? This video is for you because in our last section, what we did was just that as the instructor is instructing, right? Any point that I feel that needs to be re-emphasized, that needs more clarity, that needs need to maybe add my real world experience into it. I try as much as possible to add it so that we will flow together, right? And you can still ask. Currently now it's just only one person that is live, right? You can still as much as possible ask your question in the comment section, and I will get to see it and respond as quick as possible, right? So this is more like it will be more like an interactive stuff, right? And then for people that are already tech inclined, right, this video is for you. So this is the second set of people that this live section is for, right? Why is it for you? It's so that you can help me, right, and also attempt the questions of people that need clarity, and also you can also judge or question, my thought process, right? Challenge my worldview, challenge my thought process as we journey through, right? So anywhere you're watching this video from, right, at the end of this section, I'm sorry, anywhere you click the link that redirects you or routed you to this video, right, at the end of this video, I'll still try as much as possible to repost this link on that platform so that you'll be able to see the full live section. Right, for now, we are just 26 subscribers and we don't have much people that might be joining the live session. So I'll try as much as possible to encourage you to join the live section and also subscribe. Right, the live session will benefit you, right? That you can also ask reward question. Then subscribe as much as possible, right? If you find value on this, just subscribe, and it's a way to support me too. And then I just want to say one more thing, right? I will be starting a teaching section, right, with some students, right, from Monday, right. I'll be starting the teaching section. It's still gonna be a 1 hour section, right, where I'll be teaching them back end, right? I'll be teaching them back end, and I'll be taking them from the theoretical point of view, right, to where they'll start understanding some terminology, start to try to understand what indexes means, what async means, what logs and relogs, and what database means, what when we talk about reliability, what are we talking about? When we talk about correctness, what does webhook means? What does HTTP means? What does CPU means? What does software means? What does program running on a processor mean? What does thread means? Right? And so we want to isolate any language. We want to isolate the concept, right, from any particular language, right? And so we just it's going to be a 1 hour section every day, right? The class is a live class, it's not be on YouTube here, right? But at the end of the section, I'll try as much as possible to push on this channel, right? To update us on this channel, right? The whole section. Right, so each section I'll try as much as possible to post it that day so that you follow along. Right, the essence of the class is just for people that want to really understand how backend works. Right, you want to understand how really backend works, and also help you in your interview section, and help you understand and grasp any language, right? So language itself will now be more like a tool for you to explore your knowledge on back end, right? It will no longer be like you're trying to learn um, a language separately and you're trying to learn back end engineering separately, right? That's the goal. And at the end of the day, we usher the whole understanding of our back end with Go language. Right? Go also helps us to understand how system engineering works. At the end of the day, you just to arm the students with um, how to think or reason well, right, when it comes to back-end engineering, right? That's the goal. And so I want to also encourage you to subscribe, right? Because you will be getting more of the updates as we progress, right? So having said that, one of the things I want to do now is just to update um, um my class, the community I'm in, on Telegram. I just want to share this link there and just to give update that I'm already live, right? For anybody that really cares to join my live section, right? And also towards the course of this class, right, I will also share um I don't know why this is not again. Okay. Okay, so towards the course of this class also, I'll also share um, this link to my X community. Some of the communities on X, I'll still share it there. Right. So having said that, right, so let's go back to this video. So I hope you're with your writing material and your book and your pen, right? Because of course we are students, we need to learn, right? And if you're learning, you to show that you're a serious student, your brain can actually assimilate and capture the information. You need to jot down, you need to write, right? That's very, very important. It's very, very crucial, right? So then let's try to reiterate where we stopped last. So in the last section, right, we basically focus on the transitioning from a server. First of all, we talked about why you should learn Docker, right? The importance of Docker and what Docker is really doing. Right? This is a DevOps journey, right? We are starting with Docker. Right? Kubernetes is where things start becoming complex. We talk about um, why Docker is important. We came to understanding that Docker is important for reproducibility. What does reproducibility means that if your laptop, if your Docker, your program is working on your PC, if you containerize it, it should at the same time work in another person's PC, right? That's what, and we talked about why Docker is important, and you mentioned that is for defensive dependency management. Sorry, not defensive, dependency management. I say dependency management is when maybe your Python has a different what's it called? A different version from maybe your Flask fast API version, right? Docker helps to remove that constraint, helps remove that bottleneck, right? And so it helps on that dependency management, right? And the example I gave is when I was building a project for one company like that, right? I was building a settlement um product, right, for a company like that, and yeah, the NDA is still running. So, so I was doing this product for this company, and one of my challenge was that I built it with Coda, right? Kotlin and Java. And so my challenge was on how to manage these different versions of these tools to be able to give me what I'm looking for. Right? It was a whole lot of challenge for me. Right? I had to go through a whole lot to be able to maximize these three different versions. Right? And so Docker removed that bottleneck. Right? And The last one is portability, and so that means that you can run your container in any machine, right? You can run your container in any environment, right? You can run it in AWS. You can run the same container that you run in AWS in GCP, right? You can run it in Linux. You can run it in OS or Mac, and it will still turn up the same way, right? Then we went ahead to talk about what a server is, the importance of server and how server is important. So I'm trying to reiterate here. Just stay with me, right? So this will also help you if you watch the previous video, right? It will still help you to juggle your memory, juggle your mind on okay what we learned. So we talked about server, we talked about visualization and visualization. Right? We talked about what server is, the difference between a server and a PC. So PC is just this what I'm using right now, and what is it? It's just simply um a computer that allows you to that takes input and brings that out with basic definition. Right? Servers are kind of the amplified PC, right? They are kind of the 10x of PC. And so you can think about it as they can do times 10 of what a normal PC can do, right? They can carry now a normal PC has CPU. Right, a normal PC has a RAM, that's random access memory, has a disk, has a network interface and a GCP, GCPU, right? Some system also has it, right? Some don't, right? So, but inside of a server, if your RAM is 12 gig RAM. Inside of a server, you can have like 50 gig RAMs, right? Your server can actually house different operating system comfortably. Your server can also have a whole lot of disks, right? And so it's just more like the amplified version of your PC. And so that's the difference between a PC and a server. And so we now talked about how servers work, right? We say that a server, stay with me, please. I'm trying to rephrase here. Right, we say that a server, now this is my note. So we say that basically a server is what is powering sorry, I'm looking at the definition here. So you say that a server is basically a powerful computing device, right? And you use servers when you want to scale. So the illustration that was given in this course was that your server has all these components, right, that makes it run fast, right? And it can also have a whole lot of maybe let's say three applications instead of it, right? You can install three applications instead of your server, right? And your server can run comfortably with it, right? And so you can also scale, right? That's where scaling comes into play. Scaling has to do with you having 3, 5, 10, 20, 50, 100, 8,000, 10,000 data servers, which is called data centers, right? And we went into explaining how the dynamics of a server works, right? How the dynamics of a server, how it works, right? We went to say that a server has um, a hypersensor, right? A hypervisor, right? That's a hypervisor. And what this hypervisor does is just that it helps us, it helps create this VM virtual machine or virtual environment where your apps can run independently, right? While your apps can run independently without any and also be able to maintain, right, the versions of your PCs independently, right? That's what this virtual machine does, right? So the introduction of virtual machine inside of um, servers was to help eliminate this bottleneck. And so normally servers on their own has this issue of how to handle multiple applications, right? If you install different applications inside of your server, how to be able to maintain this application was a bottleneck, right? Maintain different version of it. For example, you want to maybe update one version without touching the rest of the version. It is kind of very expensive, right? And so let's say that you want to run only one application per server, right? That's also costly because servers are very costly, and so you want to maximize it. You want to, in fact, if there's any way you can maybe install 1 million application inside of your server, one server, to maximize its potential, you want to do that, right? By the same time, servers on their own has an issue, which is how to manage. One of the obvious issues is how to manage different application versions, right? How can they be able to manage this version, different version of the system, and work properly and without any overhead, right? That was the issue. Then the introduction of virtual machines, right, with the help of hypervisors, right, was that what this virtual machines does was to give each of our application their own personal workspace, right? Now that means you can maintain and work with a certain version of maybe app A, right? In isolation, right? App B has its own version and they work in isolation. App C also works in isolation with the help of the hypervisor. So what the hypervisor does actually is um, it creates a virtual environment for these different applications to work independently, right? And so how does it do that? How does it bring? So now, first of all, it takes the resources or the components of the server, right, and converts it into a virtual machine. And so you see something like vCPU, vMemory, vDisks, vNetwork cards, right, and vGCPU, right? I think is that VC, okay, GCPU wasn't mentioned yet, and I think it should be involved also. But you can correct me in the comment section. In fact, let's browse it. I mean, we are learning, right? We are learning. So let's browse it here. Does does um VMs for servers does VMs for servers have VGCP as they have VCPU? Okay, now they are saying that this is their definition. Virtual machines do not use standard VGCP units. Instead, it's if they need graphics or parallel processing acceleration, they use a VGPU, that's virtual graphic processing unit. Alright, so this answers our question. So this is just browsing, trying to know stuff. So then now we went ahead to, I think we touched some of the bottlenecks of this. So we talked about the fact that one of the problems of this virtual machine is that they are heavyweight and they have limited scalability. These are the and they are slow to start, right? So these are the some of the issues that was pointed out in the video. Right, so these are some of the issues we are pointed into. Now back to where we are currently, right? And so before we proceed, let's just I want to share this to our different audience, uh, so that you can carry everybody along as you proceed, right? Okay, so just a little bit extra. I've actually posted this thing to these different groups like more than 3 times today, but I've been always been disconnected from my network. I don't know why. I've been disconnected like a lot of times. I've been disconnected a whole lot of times. Uh, consider that. So, okay. So I just have to do this. So I've posted this. Let me just share it to other of my. Mm. Okay, so let me look for another group and post this. Okay. Uh, okay, so we come back to this in a minute. Just let me just finish sharing this. Um, okay, so let's go back to our video. Let's go back to our class. So now we are now back to. I've finished illustrating what we did last. So we are just back to here. So where we are now is where we are trying to understand what virtualization is, how virtualization went from virtualization to containerization. Right. This is where we stopped the last time, and so we'll be continuing here. So I hope you're with your writing materials. I hope you're with your book, right? So, like I said before, this class is for everybody. It's for you to learn and for you to participate, right? It's for you to engage in conversation. You can ask me question, right? You can ask me any question outside of DevOps, maybe that has to do with back end, that has to do with um software engineering, right? That has to do with software engineering generally, that has to do with back end fintech applications or blockchain applications, right? That's where I excel, blockchain infrastructures and fintech infrastructure, because that's where reliability is at each core, right? And correctness is very, very important. And so that's where I focus on those kind of applications, right? So, okay, so let's continue.
The containerized, the cloud native and the containerization, Docker, Kubernetes, and all that. So before we delve into this, let's find out or let's understand what is a Linux software process, or what's a software process in general if we're talking about Linux or Microsoft, Windows, and so on. So the process in Linux terms is a running instance, so an execution of a program. So let's say, for example, Nginx or Telnet or Ping or anything, any program. So any tool or any program that when it is executed, it has its own memory, it has its own CPU resources and system resources, but it is managed by the operating system kernel or the Linux kernel. So if I have Apache, for example, or Nginx or Tomcat or whatever is the program that I'm running, or maybe a calculator on Linux or Python, and then I run it, then it's going to be run as a separate process, kind of isolated from what is around it. So when we run any program in Linux like Bash, Nginx, Python, Apache, and all that, so what would the Linux kernel do? It will load the program code into memory. We're talking about RAM, the random access memory. It will allocate it a unique process ID or PID, and it will create a process to execute the code. So these are the three things that will happen each time we run a program. So each time you run a program or a tool that you have in Linux, there will be a process generated based on that.
So let's just still explain this. Let's talk about this actually. So this is just trying to explain what a process looks like, right? When you run a process, right? He's just saying that in the definition, he's saying that a process is a running instance of a program that has its own memory, CPU context, and system resource managed by Linux kernel, right? So I want to use Bash for example. So Bash, um, I think Bash is a good tool, or let's use Python. Right? When you're running any script or Nginx, right? Um, what happens is that the Linux kernel, which is the backbone of a whole lot of the internet, right, loads this program code into memory, right? And so, I know in the first section we talked about what RAM is, right? Random access memory, and what RAM is where execution happens, right? That's where programs are being executed, right? And so the it loads the program code into memory, right? Just it takes the code when you click on maybe run or execute, or when you click on search or whatever, right? It takes the program code, um it loads it inside of this RAM, right? And then allocates this program code a unique ID, because at the end of the day, it might not be only this code that might be running, right? So there might be a whole lot of processes running, right? There might be a whole lot of processes running inside of a thread, right? And so what it does is just give it a unique ID so that we will be aware of, this comes into play when you're um want to durably persist um, a request that came from the client, right? You have to give that request a unique ID, right? So that you be and return the ID to the client, right? And so what this thing helps you to do is to identify this um, um, request, or be able to query this request anytime you want. Query it whether it has been executed or is still executing or whatever that is happening to it, right? And so when it gives it a unique ID, right, it now creates a process to execute it, right? That's what happens. So when it loads this in the memory, it allocates a unique process ID, and then it creates a process that now runs and executes the code for you to see the outcome, right? That's what is happening here.
Tool that you have in Linux, there will be a process generated based on that. Why did we mention that? Because containers, when they run into Linux or Windows, they run as lightweight isolated process that is in a shared operating system. As we will see throughout the lab, that we are going to run all of that on Ubuntu Linux. So each time when you run a container, it's going to be a small size, lightweight, like a small size. It doesn't need a full operating system. We're going to get into that. And everything that container, let's say the container is for Apache or Nginx, anything that it needs in order to run in terms of code, libraries, environment variables, runtime, configuration files, they are all going to be within that process. So let's take a simple example, Python, calculator, written in Python. In order for Python to run, it needs to have the runtime. So basically the interpreter that will take the Python commands and tell the machine or tell the hardware and software what to do with it. So that with any tools or configuration files and with the code in Python itself and with any environment variables, usernames, passwords, and so on, all will be encapsulated into what we call the lightweight isolated process, which is the container. And this is why we brought into attention the Linux process, or what is the Linux process. If we put that in a visual format, let's say that the container is this box. We are just trying to visualize it. This is not, we don't have boxes in operating systems. So the code in Python, in my example, the runtime, the interpreter, the Python 3 that will run this, and any configuration files required, and any binaries or dependencies or libraries that are required. For example, if I'm running deep math, there is a lot of libraries I can load in Python that would help me with that. If I'm doing data analysis, machine learning, AI, data science, analytics, then there will be a lot of libraries I can load that will help me. All of that is going all together be put into the container, and the container will be considered the program that when I run, it will run in an isolated process. Think of shipping containers. So let's say the container on the top, if I ship that container and I put all my furniture and my appliances and all that inside the container and it is closed, now if I decide to send it to Latin America, when I go there, I'm going to find exactly the same. Where if I decide to move to Australia, the same container, then it will be shipped to Australia. When I travel to Australia, I'll find exactly the same content inside that container. So that's exactly the concept of containers, and it was derived or it was inspired by the shipping containers. And of course, we can run applications inside containers because the code we are talking about here will be more or less to do a specific program, a specific function, or to solve a problem, or maybe be part of an application. The features of containers. And the reason why we're getting into that, because we are going to take a step back afterwards and contrast that to the issues or limitations we discussed with virtual machines. So the features in containers, that they don't need a full operating system. And we're going to explain how. Each one runs into a process that is isolated, self-contained, and it has everything that it needs. It is much faster because it doesn't have a full OS and it is lightweight. It's much faster to create, start, and tear down. It's repeatable. The same one, reproducible basically. The same container, if you run it here, or if you run it in Hawaii, or if you run it on AWS or on premises, it's going to be the same thing, reproducible. And definitely, like shipping containers in shipping industry, it is portable. And it's easily scalable. Lightweight software process, then we can scale very easily. All right, so that's all great. But how can a container run without an operating system? All great, very easily. Scalable, lightweight software process, then we.
Okay, so now what is being talked about here, we are trying to define what a container is, and we say that it's a lightweight, isolated process running on a shared operating system kernel. You know, a package with everything that is needed to run. So now I want to use this box here that we are seeing on the screen to just illustrate, what we are trying to talk about here, right? Now, let's say you write a code, and the code, the what you use is Python, and the container here is the box, right? He's saying that this container when you containerize your application, it will involve the code, right? It will involve the code, it will involve the runtime that will actually execute this code. In the Python example now, the Python code, we need a Python runtime to execute the Python code, right? And also it will need some configuration. Configurations are just how you want your system to start, how you want the system to actually um, process some kind of information, some default states, right? That you know that these configurations are things that are there to actually help your system run in a certain way, right? Then dependencies, this is quite crucial, right? Dependencies, and the thing about this dependency of a thing is that the dependency that you use to run this application will still be the same dependency that will be packaged inside of this container, right? So looking at the features of this container, um, it says that it does not require a separate iOS. That does not require a full iOS for it to run, right? It's isolated and self-contained environment, right? And it's because it doesn't it's not it's lightweight, right? It's fast to create, and also you can tear it down. It can be repeatable, it is portable, and it's easy to scale, right? That's just what he's trying to say. I just wanted to just talk about that and we'll move on.
Can scale very easily. All right, so that's all great. But how can a container run without an operating system? That's what I mentioned, and there has to be a way to do it, right? In order to build, ship, and run containers, there has to be some magic that happens on the host. If it is a program software process, it has to be running on a computing device, on a server. So how can that happen? How can we run containers? Let's say this is container 1 and container 2. How can we run this on this server that has an operating system? There has to be something that would allow the container to feel that it has an operating system. So it will lean on the operating system of the host. So basically they are going to share the kernel of the operating system, be it Linux or Windows or Mac OS, we don't care. That operating system is going to serve all the containers. The kernel is going to serve all the containers that are in the same host. And that emulation or that mediator is called the containerization engine or the container engine, or if it is Docker, then it's the Docker engine. So now we have the dotted line that represents a container. It has the application code, configuration, dependencies, binaries, libraries, anything that it needs to run. And it is a self-contained entity that will run as an isolated process. So without the container engine, we cannot run containers. And notice that we don't have a hypervisor here. We don't need the hypervisor. So now we are sharing, or we are allowing the operating system to be served by the engine, the container engine, to serve all the containers. And this is how the containers don't need their own operating system. Containerized applications, as we mentioned, they run into separate processes isolated, and Docker is the most popular container engine, and it has been out for about, 12, 14 years now. Docker is available as a community edition, which is free, and it's also available as a paid edition, which is enterprise edition, or EE. All right, so Docker containers from the Docker file to an application. How can we start a container? We looked at the previous slide that there was an existing container, but where does it come from? How do I start it? How do I write, or what do I need to do in order to configure a container and allow the operating system to find out that there is a container? So we start from what we call a Docker file, a script text that you write down. Of course, it has syntax and there is some understanding and knowledge behind it. Once you have that Docker file, then it will be used to create what we call a container image. And the container image can be used to run containers across different environments. If you look at how this happens, we have the Docker file. And here's an example. It's a text file. Remember when we said one of the advantages of containerization is the fact you can do version control? At that time, I mentioned that version control is possible because it is more or less text files. So from the Docker file, we need to create or build what we call an image. And as we'll see shortly, that there is a command called docker build. It can take up a Docker file and build the image. So what's the image? That's the template from which you can create containers. Think about it like the virtual machine ISO file, for example, that from which you can build virtual machines. Now we can do a Docker run command, and then we end up with the running applications inside containers. And of course, this is, and then we the
Yeah, let me just take this
virtual
thing back a
the
bit.
big
Let
and
me
do
take
it's a
this thing
environment.
back.
So we figure a container. How do I slide
Let me
and
take this thing
update it?
back.
And Docker is the most popular container engine, and it has been out for about isolated. Containerized applications, as we mentioned, they run into separate processes isolated, and Docker is the most popular container engine, and it has been out for about, I don't know, 12, 14 years now. Docker is available as a community edition, which is free, and it's also available as a paid edition, which is enterprise edition, or EE. All right, so Docker containers from the Docker file to an application. How can we start a container? We looked at the previous slide that there was an existing container, but where does it come from? How do I start it? How do I write, or what do I need to do in order to configure a container and allow the operating system to find out that there is a container? So we start from what we call a Docker file, a script text that you write down. Of course, it has syntax and there is some understanding and knowledge behind it. Once you have that Docker file, then it will be used to create what we call a container image. And the container image can be used to run containers across different environments. If you look at how this happens, we have the Docker file. And here's an example. It's a text file. Remember when we said one of the advantages of containerization is the fact you can do version control? At that time, I mentioned that version control is possible because it is more or less text files. So from the Docker file, we need to create or build what we call an image. And as we'll see shortly, that there is a command called docker build. It can take up a Docker file and build the image. So what's the image? That's the template from which you can create containers. Think about it like the virtual machine ISO file, for example, that from which you can build virtual machines. Or let each virtual machine, let's say this is VM2 and this was VM1. So let's every virtual machine think that it has the right hardware that it needs. They were not leaning on the operating system because each one of them had its own operating system. Full operating system, be it Windows, Mac, or Linux, or whatever. On this side, we don't have the hypervisor, but we have the container engine, Docker engine. And then we have the containers running on top, sharing the kernel or the operating system. So the way they share the kernel is through the Docker engine. Now a question. Can we run containers on virtual machines? So here it's obvious that we can run it on physical servers. This is a physical server. There is no hypervisor. So
Now here is they are being called guest OS, right? And these VMs, because they have their own individual OS, right, it makes them heavy. So these virtual machines are heavy because of they have a whole lot going on already, just like Java, right? They have a whole lot going on already. But the containerization now, hypervisor actually run on top of the operating system of your hard disk of your server, sorry, right? And remember, you can have a lot of operating system inside one server, right? Then this hypervisor actually takes charge of this, and what it does is just that it takes the components of this hardware and virtually clone it across different virtual machines, and give and allocate them as much of that component they need. Maybe be it RAM, be it disk, be it network card, right? Then here now he's trying to explain on the Docker side, actually, he's trying to explain that the hardware and the operating systems are the same, right? But the container engine, right? In our case now is Docker. He based on what he was saying, That means that Docker is not the only engine, available for containerization, right? And so, but Docker is popular, right? That's what he's trying to say. Then we are saying now that this Docker, what it does that is just that it shares the same um OS with the host. So this host now might be using, let's say you just want to use Linux, right? It will share the same host with you and create these containers, right? And he mentioned something, the flow of this building this container is, first of all, you writing a Docker file, right? And so this Docker file, when executed, you will build what we call an image, right? So it will kind of be a template to build a container, right? And so what that image does, right, is also what gives you access to build all these containers. Now, the beauty here, right? The beauty here, I just want to expand on this Docker end, right? So that maybe you understand the way I'm understanding, or you have to maybe have an idea the way I'm having this idea, right? This view, right? Now the beauty of this now is just that, when we talk about that this is portable, you can run it in if you run in PCA, right? It can run in PCZ, right? It doesn't matter, it can really run. Now, what really makes this what it is this Docker engine, right, that builds the image. Remember, he said that you can actually um replicate this image. It's reusable. The images are reusable. You can use it as many times as you want across any device, right? It's reusable. That's what these images are for. They are very, very reusable. And the Docker engine only uses your default OS, right? That's what it uses. It uses a shared host OS. So the host is the server. It uses the OS of the server to produce the containers, right? And it doesn't really have its own um, operating systems like the hypervisors here, right? And now he was trying to explain if you can run Docker engine inside of this hypervisor. That's what he's trying to explain. Let's continue.
That is absolutely a physical server. Now, can I run it on a virtual machine? And the answer is absolutely you can. And if we put both together in one drawing, it will be exactly like what we see now. So we have the hardware, the operating system. This is the physical server. And then I have the hypervisor, which can create VM1 and VM2. In one of the virtual machines, which has a full operating system, I'm going to install Docker engine, a container engine. And the container engine will allow containers to share the guest OS in this time. So they don't have anything to do with the external operating system on the physical server. On virtual machines, because we had the fact or the issue or the limitation that virtual machines are heavyweight, slow to start. And that's why containers are lightweight and they start in milliseconds. Virtual machines have limited scalability because of the physical host's limitations. Containers, they have much faster scaling and they don't take much time and they don't take much space as well or resources. Virtual machines are low in portability because of the reproducibility limitations, whereas containers have excellent portability. Virtual machines, I have one operating system in each one of them, so that's more resources consumed by the requirements of the operating system, whereas in containers, they share the operating system of the host. Here we have inefficient image management. Part of it is the size and the variations between the different environments, whereas here it's efficient image management, and we will find out later about Docker Hub and repositories or registries where you can ship your built images and then they can be pulled for whatever reason in whichever location. This one has poor development tested production, basically environment parity. will be poor, whereas in containers, since they have everything within, they are excellent for different environments and for CI/CD applications as well. So what are examples of the popular CI/CD applications as well?
Okay, so I just want to talk a bit about this, right? Now, I just want to pick out some few of it and talk about, right? The difference between the VM machines and the containerization. Now, when we talk about heavyweight slow, right? We meant that the previous image was talking about this previous slide actually, was talking about how that the VM machines actually have each VM, right, has its own OS, right, its own full OS, which is called guest OS, right? That's what makes it very, 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 very heavy, right? And containers are lightweight because they only shared the host operating system, right? And we talk about limitation in scalability and fast scalability. So limitation in scalability has to also do with the complexity that comes with um, it not being portable, right? And it's being heavyweight, right? We talk about low portability and excellent portability. Low portability is just the fact that you can't scale this in to scale this in another environment. To scale virtual machine in another environment might be a little bit hard, right? It will be a little bit an overhead, right, compared to when you're doing it on a container, right? We talk about redundant OS overhead, right? Now, this redundant, that's where I wanted to talk about. I want to just pay close attention. Now, when we talk about redundant OS overhead, remember in the VM machine, right? I feel like just drawing something. I don't know. Let's since we are learning together, right? Let me just
Are excellent
now
for
let me just see if I can do some drawing. Just stay with me, please. Stay with me. So draw. Yeah, so I use this when I want to do any illustration actually. This Excel draw whiteboard. So let me draw something. This is my previous. Let's slide down. Let's slide down. This is my previous works. Okay, so this is what I wanted to say. Right, just pay close attention. Now, um, we are saying so our explanation was on the fact that this redundant OS overhead. Now we are talking about redundant OS overhead that is in the VM machine. Now this is what we are talking about. Now remember that each VM machine. So let's say that this is a VM machine. Like let's say V1 VM. Let's call it VM1, right? Let's call this VM2, right? VM2, right? Let's call this VM2. Now, these are two VMs, and each of these VMs have its own OS, this own operating system OS, right? They have their own operating system OS, right? And they are being called the guest OS. Then we have the lower layer is the hypervisor, right? That actually gives them room for them to work individually, right? And just what it does is just to share the components of the server, which include the CPU, the RAM, and the rest, right? And beneath this hypervisor, we have another OS, which is the OS of the server, right? I don't know if you understand. And so in the containerization we are talking about, the containerization, now this is for virtual machines. This is virtual machine, right? That when you talk about containerization, containerization on its own has, let's say these are two containers, right? Let's say C1 and C2, right? This is C1 and C2. Right, so these two containers actually have um only one operating system that is sharing with them. And the operating system that is being shared among these two containers is the operating system of the server, right? And so we have hypervisor on our left here, which is for VMs, but um, in containers we have what we call container engines, right? Container engines, right? Which in our case we are focusing on Docker, right? And so this container engine, these containers actually share the operating system of the server, right? Now the server has its own operating system, right? That is pre-installed, that is living on the server itself, right? So instead of this Docker or this container engine having individual iOS, sorry, individual OS, that's operating system, like this VM machine. What it does is just to just share the already existing the host operating system. So why you call it host, why you call this server host is because is this server is what is hosting this our container engine, right? So that's what is happening here. So when we say that that this VM machine has redundant OS overhead, we are saying that there is no need of having individual OS for individual VM machines, since the OS, the host server has an OS already. And so this OS also brings another overhead, brings is makes it expensive. One, it makes it to be heavyweight compared to the container engine side, right? So this is just what this is trying to explain. There is nothing else. That's just the simple explanation. And so we are trying to, and also try to say that the Docker file is the Docker file. Right? We have what you call the Docker file. The same way we have a what is it called? A code base, right? A code, your code. You write a code, right? We have a Docker file, and this Docker file, when we run it, it builds an image that also helps us create these containers, right? That's how we come about building containers, right? So you write a Docker file, you build the image, and so this image you can run it in different, you can reuse it as in different environments, right? You can reuse it in different environments. So that's what this is. So let's go back to our video and continue our class, please.
different environments and for CI/CD applications as well. So what are examples of the popular container engines and runtimes? We have Docker, of course, that is going to be the course. And then we have Linux containers, and these are more low-level containers. That was before Docker, the LXC or Linux containers, and they are system-level containerization framework. Then we have Containerd, which is geared more towards Kubernetes. And then we have CREO, which also is geared towards Kubernetes deployments. Let's talk about Docker architecture. What are the components that make up what we call a Docker host at the end? What are the different software components that play within the container engine or Docker engine in order to allow us to perform or to use Docker and create containers and tear them down and so on? So Docker is a software platform. The Docker engine that we discussed is a software. It's not a hardware thing. That simplifies creating or building, running, tearing down, and while it is running, managing the containers or applications in containers at a scale. It is developed by Docker Incorporation, and it's an open source software, and it virtualizes, as we mentioned, or allows the sharing of the kernel, the host operating system. And the applications running in containers, they will be running in isolated environments, the processes that we discussed. And Docker can be a community edition, which is free, anyone can play with. And there is an enterprise edition that has additional features, but you have to pay for that. So what are the components within a Docker host in order to be able to use it efficiently? Number one is the Docker client. That's the interface. When you type anything, any command that starts with the keyword Docker, then that client is going to understand what you want, and that is going to send in the request to the next component. So it enables developers, users to interact with Docker. That's the interface that you have. And we can run commands like docker pull, docker run, docker build. Don't worry about that. We're going to find about it later on. And we use command line interface to do this. So when we use the Docker commands, what happens is the client is going to understand what you want. It will validate it, and then it will send it to what we call the Docker service or the Docker daemon or Docker D. We're going to talk about this next. The next component is the Docker. We're going to talk about this next. Docker service or the Docker daemon or Docker D. We're going to talk about.
Now, this is what we are trying to demystify the architectural design of Docker, right? The Docker architecture, what makes Docker what it is, right? And so we first of all started talking about that the Docker clients, right? And what Docker client does is just it enables developers like us and other users to interact with Docker, right? Using the Docker pool, when you do Git ignore or git commit, git push, all those keywords. That's the same way Docker have a CLI that helps you interact with the with Docker, right? And so when you use those commands, right, it's saying that when you use the commands, the Docker client from the UI, right, sends those commands to the Docker daemon or send it to be dockered. Right? So yeah, that's what it is. I want it to sink a bit. I just want to allow you to allow this now to sink a bit, right? Because this architectural design is very, very important. Like when you talk about architectural design, right, it's quite important for you to understand how the architecture of something is, right? It will help you, right? Instead of you to start running into implementation, right? It's good for you to understand how does this thing work under the hood. How does it implement? What's the implementation? How does data flow? Right? It gives you enough confidence to try to manipulate and evolve and be creative enough. Right? That's why I want this thing to sink a bit. So let's see it raise. We say that the Docker client is just a place for you to interact with Docker. So he said that when you send out those commands to Docker, right? When you send out this command to Docker, the Docker client sends these commands, right, to the Docker daemon or to be Dockered, right? I think I like the word Dockered actually. Okay, so let me just write this thing down. So I'm still writing. I have my notes here. So I have my notes here. I'm still writing. Alright, so let's continue. So I think these have actually started well.
About this next. The next component is the Docker host. That client, where does it exist? I need a host. I need either a virtual machine or a server in order to install the Docker engine, and then I will have the CLI. So that thing is called the host. The virtual machine or the server where the Docker engine is installed is called the host. And as we mentioned, it can be a physical machine, physical server, or a virtual machine. Then we have the Docker daemon, or the name is Docker D, which is the heart of Docker. That's the brain of Docker. Then we have that's the brain of Docker.
So I'm pausing to just assimilate this thing and take down some notes. So he's saying that a Docker host is the server or the virtual machine on which the Docker engine is installed, right? So that's what it. I think this is self-explanatory, right? It's self-explanatory. And so the Docker engine itself. So the servers or the virtual machine we talked about is the servers. Let me go back to this image. I'm so sorry actually, but we need to, we need to get this. I'm doing this thing also, especially for people that are coming from another sector actually. And so, where these things are being installed are called the Docker being the server, right? This is a virtual machine on which the Docker engine is installed, right? They are being called the Docker host. So a server is a Docker host, can be a Docker host. The virtual machine can be a Docker host, right? I will now say that the Docker daemon or the Docker D. I thought it was Docker. I said Docker D. I heard him well. Now I said Docker D is the heart of Docker. So you need to pay attention to this Docker D. It's very, very important to pay attention to this Docker D.
Then we have Docker images. So we start with a Docker file, we create the images, and then we create the containers. So the images or the templates, these are read-only binary templates, and we can use them to build containers, and they are reusable. I can build 1 million containers from the same image, and it's not going to vanish or expire or be depleted or anything. So the templates, they define the application code, where to get it or download it from, any libraries required, any dependencies, any configuration files, any environment variables, they are all going to be in the image, and obviously they must have been in the Docker file, which was transformed into an image, and now we can run the application that this code is building inside containers. So inside the host we have the daemon, and then we have images. So I can have multiple images on my host. Okay, let's zoom. I can have multiple images.
So I just want to capture this well, right? Just stay with me. I just want to capture this well. I'm learning actually. I'm not rushing anywhere. So this will also help you to get to know how to follow classes, right? You can wind back. Can go a bit front, right? And I'm still following the comment section, right? If I see any question here, right, I will do well to answer it, or if you want me to go back, if you want me to go front, I will do well to do that, right? And so he said that the container they contain the application code, libraries, dependencies required to run an application. So what he's saying is that a Docker file, so the daemon or Docker D is the heart of Docker, right? And so when you run your Docker file, right, it creates image. And so what is the an image? An image is a read-only template used to build many containers, right? That's what an image is. So I think that this image uh, the ability to build an image, right, is inside of this daemon or inside of the container engine, right? And then what is the content of the image? So the content of the image contains the application code, libraries or dependencies that you install. So I write more of Rust and write more of Go language. So let me use Rust to illustrate this, right? The application code, we have some dependencies you installed inside Cargo um, um, that actually helps your application run, right? So the image will contain that full will house the full essence of your application, right? And he said this is also saying that you can build as many images as you want, right? You can build as many images as possible, right? So that's clear. Let's continue.
Is on my host. Okay, let's zoom into the Docker daemon to find out that heart of Docker. What exactly does it do? So the Docker daemon is going to wait for API requests coming from the client. We mentioned that the client, well, as you type commands, it will validate and then it will send in requests to the daemon. And then it will create containers and it will manage them. It will create images, networks, and volumes. Okay, so the daemon is going to be the heart of all this. Is it itself going to create that? Hold on. We're going to come to which component exactly within Docker that is going to do the actual creation and management of containers. Also, the Docker daemon will build container images as requested by the client. When you do the docker build command, it's going to build images from the Docker files you are pointing to. And it interfaces with the Docker registries. So it is the middleman between the client, the registries, and what happens on the host. So when it interfaces with the registries, it's either to publish, we have created an image, let's put it on the registry so people can benefit from that, or to pull an image that doesn't exist but I need it. So as requested by the client, the Docker daemon will be able to do all of this. And it will manage the life cycle of the containers from starting, stopping, deletion, or removal. All of that is also managed by the daemon. Starting, stopping, deletion, or removal. All of that is also managed by from starting, stopping, deletion.
So now let's talk about this demon. Now, I'm still taking notes. I hope you're taking notes. I hope you're taking notes. Right? It's very, very important. You can still go back to your notes and try to understand. Right? Taking note of the key points. So he said here that Docker daemon is the heart of Docker. It listens to the Docker API requests, from the Docker client. And we said that the Docker client is what helps you interact with Docker, right? When you maybe write writing those commands, Docker build, Docker pull, right? It listens to those requests from the client, right? And then it also manages the containers, right? So this Docker daemon listens to your request, what is coming from the client side, right? It manages containers, right? It manages containers, it manages images, it manages networks and volume, right? So volume is just more about how many of the activities, how often activities is happening instead of this um, container, right? And it also says that it builds container images as requested by the client. Let me jot that down. It builds um, container image. It builds container image as request by the client. It interfaces with Docker registrars to pull or publish images as requested by the client. So this sits between your file, your Docker file, and the registrar. So it interfaces with Docker registers to pull or publish you pull or publish images as requested by the client. So it manages the life cycle of the containers. So the life cycle of the containers is just from when you talk to the Docker engine from the client side to when everything happened, to the whole process, to when the process stops, to when the images are being deleted or removed from the engine, right? So it manages the life cycle. And so for me now, I don't really know what a registrar in this case is,
or
Docker
removal, all of that.
registrar. So what I want to do is just to browse about it, you know. What is Docker registrar, right? What is Docker registries? Oh, regis- So he said that a Docker registry is a centralized storage and distribution system used to upload, manage, and download Docker image. So what Docker registry is in simple terms is just that it's a place where you can upload, manage, and download Docker images. So Docker registry. So it's a centralized storage actually and distributed used to upload. So I'm tempted to call it a what's it called, a database kind of, right, where you can be able to, or you can upload and manage and also download named Docker images. So activities that happen there is maybe when you want to reuse an image, you can actually download an image from there, or download image or you reuse, like, is where you can store your images generally, right, for later use, right? So he says here that the registry actually over racking hosting services, right? He also said that the repository, a collection of dated images or versions with a registry, Ubuntu repository. Okay, maybe we'll soon find out. But now this is the whole idea of registry, just where you can store your images, right? Yeah, we've understood that. Let's go back to our class.
That is also managed by the daemon. So if we have the image and we have the daemon, which are inside the Docker host, then we can start building containers. So containers are nothing more than encapsulated environment which you can use to run applications. A container runs as a process in an isolated environment. We know this. It packages, the container packages the application and its dependencies in a single executable unit, the program or the process that runs at the end. Dependencies in a single executable, it packages container related, we can
Let me
start
go
building
back to this. Let me go
containment.
back to this, please, please, please.
So if we have the image and we have the daemon, which are inside the Docker host, then we can start building containers. So containers are nothing more than encapsulated environment which you can use to run applications. A container runs as a which you can use. So containers are inside the Docker host. Then we have the daemon by the daemon. Starting, stopping, deletion or removal, all of that is also managed by the daemon. So if we have the image and we have the daemon, which are inside the Docker host, then we can start building containers. So containers are nothing more than encapsulated environment which you can use to run applications. A container runs as a process in an isolated environment. We know this.
So what is an encapsulated environment? When we talk about container, let's just browse about that too. Um, So I really want to get let's understand it. Me, I don't know it. I don't know what an encapsulated environment means. I will find out together. So an encapsulated environment in Docker is a safe, isolated space for running applications. So it's more like a process, right? So we can say that we can say that a our first definition about RAM, right? Let me go back to sorry, let me go back to that place because there was something we defined earlier on how we can there was a definition with something we defined earlier on. I'm looking for that, right? Okay. Okay, when we are talking about a process, yes, we're talking about a process, and we said that a process is a running instance of a program that has its own memory, CPU, and system resources. Is managed by the runtime. Right, I think that's what was talking about. So the runtime we take that code, right, and put it inside and I think he's put inside an execution inside the RAM, right? I'm sure it's inside the RAM. I'm trying to think here. I'm so sorry. I'm trying to think here, right? Then it's from the RAM, it gives the process an ID before it is being executed, right? So that's what I can actually think of my head here. Right. But this is what an encapsulated environment means, just an environment where you can run your application, just like a process, right? That's what it is. That's what it means.
It packages, the container packages the application and its dependencies in a single executable unit, the program or the process that runs at the end. All right, so since we talked about the daemon and the client and the host that runs at the end and its dependencies in a single executable.
So let's finish this one. We say that a container is an instance of a Docker image. A container comes as a process in an isolated environment. We also say that it packages the application and its dependencies into a single executable unit. I really want to bring you because I think he touched this um this thing actually before. He touched it and I wrote it down. So I want to see if I can find it. I can get a hold of it. I can't really find it actually. Okay. I can't really find it. I can't really find it here, sure. But you mentioned it.
Unit, the program or the process that runs at the end. All right, so since we talked about the daemon and the client and the host, and we talked about the images and the containers, then we need to also highlight the registries where we can host and store Docker images. So if I have an image, then I can, if I create the image, then I can ship it into the registry. So it will be safe. If my laptop crashes, then it is in a safe place. I can provide the link or the URL for others to download that image and use it. And I can make it public if it is something unique that it doesn't have to do with my corporate and I'm building and giving back to the community, then it can be published as public and everyone can benefit from that. Docker Hub is the public registry that anyone can use. So that's the most famous registry that is available to date. When needed, we can pull images to the host from the registry. So this is going to be within the host, and then we can pull images if we need them. For example, this is a brand new host, and I would like to start an Ubuntu container. So then I need an Ubuntu image or Nginx or Apache or whatever. And users can also push their created images to the configured registry. So again, I am pushing from the host out, or I am pulling into the host. So pushing and pulling images. We put all of that in one images into the host. So push.
Let me just copy the register there, please.
Pushing and pulling images. Or is to the Nginx or Apache to start an Ubuntu container. So then I need an Ubuntu image or Nginx or Apache or whatever. And users can also push their created images to the configured registry. So again, I am pushing from the host out, or I am pulling into the host. So pushing and pulling images. We put all of that in one page so it becomes easier for us to deal with. Then we have the client, we have the host with the Docker daemon, we have the registry where we have all the images that we need if it was Docker Hub, or it could be a private registry for the corporate. So we have all the images we need for the corporate. So most probably we have built them and now we are using them. So if I have a Docker pull command issued by the client, the request will go to the daemon. The daemon will head to the registry. If it is not available on the host, then it will head to the registry to see if we can find it. Let's say, for example, I wanted Docker pull, I wanted to get an Ubuntu and a Postgres database. Then the Docker pull will bring in these images and they are going to be on my host, download them on my host. Now, since I have them, then I want to start building the container. So I can do Docker run, and Docker run will go through the daemon again from the client, and we'll use the images that we have downloaded to create an Ubuntu container and a Postgres container. And of course, if we have the Docker files, we can build our own images as well. So that is something also we can do. And the request will go to the daemon. The daemon will know which Docker file, will pull it, and then we'll create an image. And then I can push the image into the registry as you might have guessed it. All right, let's find.
Okay, so this is where we'll be ending our class for today. I hope you learned something, you had something in your head. I think this class is a very good foundation. You know, he was talking about trying to understand the architectural design of what Docker looks like. It's quite important. Like I said, you know, understanding how something works from the hood is very, very vital. It's very, very important. You know, throughout your journey, it's very, very important. It's good for you to know something at the foundational level, right? So that if you want to innovate from the top, you already know how the foundation works. it will be easier for you to navigate and also explore, right? So that's just it. But we will continue tomorrow actually. It will continue tomorrow. And so to reiterate, what was the major thing we actually focused on was talking about the difference between a VM machine and a container. Right, we talked about that a VM machine can still host a container, right? And we now focus more on the architectural design of a container, right? That's what we now focused on majorly, the architectural design of a container, how the container works. And we say that the container has three parts: the client side, the daemon, and the registrar, right? And so we say that the you can actually send a command from the client side into the daemon. And then we say that daemon listens to API from the client side, right? And it manages image containers and the rest, right? And the registrar also. So maybe you send a pull request on the clients from the client to the daemon. The daemon will check we check if the request you sent is available, or if the image is available, right? If it's not available, it will go to the registrar, right, to pull that request for you, right? It will go to the registrar to pull that request for you. And so he talks about the Docker Hub. In fact, we'll talk about Docker Hub later. So when it pulls the image for you, it will actually build that image inside of your um, engine, right, inside your local host, right, and then containerize it. And we talk about containers as processes, right, where your application will run, where your built application can run, right. And so each image has its own container, right? Each image has its own container. Each image has its own container. That's what it is, right? And then if your engine or your host already have an image, you send in your command, your Docker build, and it will build your image. And then for container sake, right? So building an image, when the image is being built, a container should be provided. So what the container does is just that it gives you a place of running your application, right? Like processes, like instances actually. So yeah, that's just it. Then hubs are a public place where built images reside, right? Where you can upload and pull your images, right? Yeah, so that's just it. I'm just trying to paraphrase what was being talked about, right? Yeah, so that's it. See you next time. See you tomorrow, hopefully. That we'll have an amazing time as we did today.
Find out